So it looks like I'm back on the air after a momentary hiatus. I got a new microphone, so if it's too loud or too soft, please let me know. Today we're going to be talking about metamorphic rocks and how other rocks transform into metamorphic rocks through various processes that occur beneath the Earth's surface. We know that the three primary activities, or the three major ones, are going to be heat, pressure, and fluid activity, and these are the three agents of metamorphism. We also have three different kinds of metamorphism that we talk about. It's contact, dynamic, and regional metamorphism. And these metamorphic rocks that are formed through those three processes are divided into two groups, foliated and non-foliated, and we differentiate those primarily on texture. Metamorphic rocks with foliated texture include slate, phyllite, schist, gneiss, amphibolite, and migmatite, and it's in that order that they go from being early metamorphic rocks to late stage metamorphic rocks. So it goes slate, phyllite, schist, gneiss, amphibolite, and migmatite. Metamorphic rocks with non-foliated texture include the marbles, the quartzites, the greenstones, the hornfells, and the anthracite, which is coal. And we're going to talk about how we can look at metamorphic rocks and group them into metamorphic zones based on the presence of index materials, which these are usually minerals that form under specific temperatures and pressures, with the presence or absence of water, in some cases like zeolite. The successive appearance of particular metamorphic minerals indicates increasing or decreasing metamorphic intensity. So let's move on to the next slide. So here we have the Taj Mahal. The Taj Mahal is made out of marble. And the reason most architecture and sculptures actually utilize marble is because it's a relatively soft rock. It's a metamorphic rock, and I think it comes in at a 3 or a 4, so it can be sculpted relatively easily with chisels and things like that. The problem is it's also soft and dissolves in acids because it's primarily, think of calcite. When you drop vinegar on your calcite or hydrochloric acid on your calcite, it's going to elicit effervescence, or carbon dioxide is going to come off of it, and we know that there's carbon dioxide in the air, and because of this, the water or the rainfall is actually a little more acidic than neutral pH because it has carbonic acid in it by absorbing that CO2. In a sense, it etches or removes marble. So that's why if you look at old limestone or marble headstones, they tend to dissolve relatively quickly, where if you make it out of something harder like a quartzite, which is almost impossible to make a headstone out of because it's so hard, it will be around for a very long time. But metamorphism is an important process that are closely related to plate tectonics because of the movement of the plates and movement of these sedimentary rocks closer to areas of heat and under higher pressure where they can undergo change. So metamorphism is basically the transformation of these rocks without melting. It's usually beneath the Earth's surface. It can be close to the Earth's surface, but it's almost always underneath, unless, of course, we're talking about a meteor impact, which is at the surface of the Earth. Basically, during metamorphism, rocks are subjected to heat and pressure, and there's a presence or absence of water, which then, or other fluids that can change their activity, their plasticity, or their elasticity. In effect, it changes the mineral composition or the texture, or both of those, and this all occurs below the melting point of these minerals, so they don't melt. They are sort of plastic. They go through chemical changes, but that's due to interlocking composition of the crystals close to them, and they actually will go through a chemical reaction with other minerals that are nearby because they're pushed closer together and put under conditions that cause chemical reactions. If you're interested in the presence of metamorphic rock, let's say you want to, I don't know, open up a quarry and find metamorphic rocks that you want to use for building materials or whatever. If you go to areas where we suspect metamorphism to occur, you have these big igneous intrusions like the shields, this stuff in purple, and then you'll have mountain ranges like we have right here, which would be the Appalachians, and you'll have areas that are close to, like Michigan, for example, that are close to the Canadian Shield or the mountain ranges of 250 million years ago, causing the sedimentary rocks in the basin to undergo some metamorphism. Now, be aware that the Michigan Basin has been around for a very long time. We're talking, a billion years. And so there's been a lot of opportunities for the sedimentary rock to become metamorphic. If you look at this figure, you'll note that they have the Rocky Mountain Range not listed, but I guess displayed. And that would be out here, because this is North America. And then we have the Andes, and they also have the continental shields. Africa, some areas right here where there's some mountains down here in South Africa. And then of course we have the Alps right in this area, which you guys did a little laboratory on. And then we have the Caucasus and the other mountains in sort of what we would consider the Eastern European countries. And then we have obviously the Himalayas. The Himalayas don't actually have as many metamorphic rocks that are subject to heat and pressure. Pressure, yes, but not heat, because it's two continents running into each other. But then of course we have the Antarctic shield and then some materials down in Australia. And you'll note these metamorphic rocks are going to be pretty much wherever you look. And so it's fairly easy to find them. As I said, there are three agents that contribute to metamorphism, or the three major agents of metamorphism. And these are heat, pressure, and fluid activity. And what this figure shows you is we have a lava flow and an ash layer. So this is the ash layer right here. This is also still the ash layer, but it's been baked by the lava, which is right here. This lava flow. What happens is the lava flow, so the volcano erupted, produced a lot of ash, and then the ash fell faster than the lava, obviously, and cooled down, and you have this whole layer right here, sitting here, and it all was white, like the ash right here, like all of this stuff. And then the lava flowed over the top of it, and you end up getting a baked zone, which means that you're going to have some contact metamorphism, like right here. Let me get a different color. So you're going to get some contact metamorphism in this area. And it's in a very small area, but you're also going to get some dynamic changes or regional changes the farther you get away from the lava flow. And then eventually you just end up with, well, the ash that's over here. I'm going to erase that slide. If you look on the lower right side of this figure, you'll see these styrofoam cups. So this is a styrofoam cup right here that we would normally, expect to find if you went down to a local supermarket or something about styrofoam cups. And they dropped it into the ocean to show what pressure does to material that has air spaces or that might not be compressed as well, or not as well, that's the wrong term, as they use the styrofoam to signify unconsolidated or maybe compacted materials, but they still have some air spaces in them. And then they drop it down to, in depth. And I think the depths are written on here, and it says in the book. When they get down really deep, all of that space and everything else is crushed out of the styrofoam cup. And you end up with something that is completely different. It's actually a plastic rather than a styrofoam. And this slide gives you an idea of what the different regions look like. So you end up with this huge, when we talk about the granite pluton, that would be the magma chamber, and it's cooled now. An aerial is just defined as a figure of radiating color coming from a central point. In this case, the granite pluton would be dark in color, obviously. I mean, humans have areoles on their breasts, which is just a darker color radiating from a central point. That's by definition what it is. And here in geology, it means the same thing. We have a darker point that radiates out, and it's basically defined as the area where the pluton interacts with the surrounding country rock. In this case, we would call the granite pluton the intrusion, right, because it's coming into the country rock. And we can see where we have the contact zone, right? This is this area right here with the different kinds of hornfels. That's a contact metamorphism. And you have this intermediate, might be dynamic, but it's an intermediate zone where you get biotite and some other things getting linked together causing different colors. And then there's this regional or external area where you're getting some metamorphism, but it's going to be under different temperature, probably lower temperature and pressures than the areas closer to the granite or to the magma chamber. In most cases, when we talk about contact metamorphism, we're basically saying how big or the size of the areal is going to be dependent on the size of the intrusion. How big is the magma chamber? The temperature of the intrusion, mafic magmas, if you remember, are hotter than the felsic magmas. The mafic magmas are around 1200 degrees, felsic around 900, and the amount of fluids and water that are found in the areas where you're getting metamorphism could be near the ocean or where there's subduction, or it could be an area where there's a lake. Like, for example, we find some really pure zeolite out in Utah because of Lake Bonneville, which means the water was present during, I mean, Yellowstone's still there, but there's some still metamorphism going on deep down in the earth, and there's still fresh water there, producing zeolites near the surface. Best example of dynamic metamorphism is where you have faults, and these areas near the fault, and I'll show you in a second, it's called an accretion wedge, where you get a turning over of this rock and high pressure builds up, it changes, it can shift. Temperature tends to be lower. In this case, I think this is a myelinite. That's what I have in the notes, but it's a fine-grained rock in faults that result from a grinding and crushing during fault movement, which then changes, metamorphoses those minerals and changes what the rock is, what kind of rock it is. And remember, that's heat, pressure, and fluidity that we're talking about when we talk about metamorphism. Those are the agents of change. And here we have all of the different conditions under which these metamorphic zones would develop. And you'll see why this is important when we actually look at the metamorphic series that starts out with slate and phyllite. So where I was just talking about where you get the dynamic metamorphism is in this wedge right here. As these move down, you end up getting a lot of high pressure, but the temperature is going to be low, because you're not really close to this magma material, the magmatic material that's right here. Sorry, it's magma, not magmatic, because that would be a rock. So that's really where most of the dynamic metamorphism is occurring. And then we have low temperature, moderate pressure up here. This is a zeolite usually in this zone. You have diamonds, metamorphic diamonds and stuff that are produced from impacts, and then just a variety of things. But there's many different temperatures and pressures, and then the presence of obviously seawater and some other stuff going on where you end up getting different metamorphic rocks, even though you have the same rock that you start with. So when you look at the indexes and other minerals during metamorphism from that figure I just showed you, we know that as temperature increases, you end up getting higher grade metamorphism going on. And as these things change over time, you'll see right here we have shale that starts out, turns into slate at relatively low temperature right here, 150. Now this is over a long period of time. And the clay, well, it's just unearthable clay that is the shale, and there are feldspars and quartz in that as well. As the pressure increases and the temperature, or it could be temperature and the pressure doesn't change all that much, you end up turning it into phyllite, where all of these different silicate minerals are starting to get realigned. And as you turn it into schist, you end up getting, the biotites, the muscovites are producing, and every once in a while you'll find these garnets. If you go over to near Philadelphia, they have a river that has a whole bunch of schist full of garnets in it, and I actually have some in the lab, but I usually go down to Pennsylvania and collect, and they have something called the mica schist zone, which is a huge area where it's just mica schist, and I have a bunch of that in the lab. If you guys ever are interested, you can get a hold of me, I can show it to you. And then we have the last thing here is the gneiss, and that is pretty high grade type of metamorphic rock. And it's used for a variety of things like building stone. It's not really as strong. We tend to use more of the sedimentary rocks for a lot of building stones. But the metamorphic can be used as well, areas where you can break it because they're not cleavage zones. They're just areas where you can break along a plane. And then the last one here is migmatite, and that's basically where you start getting flow lines and stuff like that, and it starts melting before it becomes magma out here, right? And we use these different minerals to determine what kind of metamorphic rocks we have. I mean, the index minerals, like there's the chlorite schist, they tend to be the green schists. You get the blue schists as well, the muscovite, biotite kind of schists. They're very old though. We know that these minerals form under specific metamorphic temperatures and pressures, and then the chemistries of the rocks basically affect how the formation of these index minerals. We know that the materials that are not index minerals, in this case we have feldspar and quartz, they're present throughout the whole process. They may change in quantity or crystal size, etc., but they're still quartz and they're still feldspars. Remember that muscovites and biotites, muscovite is a little different than biotite, and the garnets they have different, muscovite and biotites are sheets. Chlorite's a little bit different, but it still starts forming sheets, very small sheets, before these get aligned and you get the bigger sheets of silicate. This picture gives you an idea of what's going on and how we classify them. So we start out with a rock, and it has a random arrangement of elongated minerals because they just precipitated how they did. And then there is a pressure that is applied, and it can be from the sides, the top. I mean, it can be all the same, so that the random arrangement actually doesn't change all that much, and you just get different minerals in the end. But in this case, they're showing you how you end up with a banding pattern. In the foliated, the ones that are foliated, you can actually see them, and you end up with this, elongated streaking that occurs. Foliated textures are filled with minerals that we call platy, like plates, right? So platy minerals, and they're platy minerals, which means they're flattened out minerals because of the pressure. Non-foliated textures don't exhibit any kind of this orientation of the minerals. I mean, they may have undergone this kind of pressure, but they don't orient the same way, and so they don't look like they have any kind of orientation. There will be some streaking in some, like I've seen marble that has black streaks in it, and obviously their pressure came from two different angles, two different sides, but it doesn't actually arrange itself that way because the calcite just doesn't crystallize in that manner, and the minerals tend to be randomly oriented. So the next slide, 8.1, and this is basically just showing you the metamorphic rock, the foliated and non-foliated, and the kind of minerals that we typically find in them, and then what grade they are. It's usually associated with basically the lab. That's why I want to show it to you. So the characteristics of the rocks and the parent material. This is all the stuff that you can use when you do the lab. So it's a good table to take a look at. Moving on, we are going through rock classification. So the foliated metamorphic rocks basically have aligned minerals. They form a graded series, and that's dependent on grain size. Phyllite, which is early in the grade of metamorphic rock, has small grain size for its different minerals. And then as you move further to the right from that figure where I showed you all the different kinds of index minerals, they become coarser as they grow. So you get a coarser grained schist, and then when you get the nice, I think they're probably listed as 1 millimeter or larger if you look at the minerals, but they might be aligned along a plane. The next slide shows you pictures from the book where you end up with different schists and gneisses, and then the one on the right is that has a garnet. Those are garnets in the gneiss that you can see, or actually schist most likely. I don't know what it calls it in the book, but the minerals that are in it will determine if it's a schist or a gneiss, the size of the minerals. Sorry. And then the last figure where we're showing foliated metamorphic rocks, you end up with flow lines, which are areas where they're undergoing melting, and you start seeing a change in the type of rocks that you find. And this would be the migmatite that I talked about. And in this case, if you look, you start getting flow lines, which means they start melting and they no longer have their banding pattern, and you end up getting, this looks like granite, starts forming. There's obviously looks very much like granite over here where I'm squiggling all those lines. And so what you see is what we call flow lines, where it's starting to melt and turn into magma. And this is, it cooled now, but it's going through some partial melting. And we also have amphibolite. Amphibolite, is another fairly common coarse-grained foliated metamorphic rock that started out as an igneous rock. We have a lot of that in Michigan. We have what we call the metamorphic metagranites, which sounds really weird because we're saying metamorphic, which means above form rock, and then we're saying it's above granite because basically these are granites that didn't go through any kind of erosion producing a bedding plane. They were just granite, and then they ended up going more heat and pressure, and they realigned all of those, minerals, and we end up having a lot of the cobblestones that we find around Michigan surviving glaciation because they're a lot tougher than the granite from which they came before they metamorphosed. Moving on to the non-foliated metamorphic rocks, which are just rocks that don't have planes in them or folds. So the first one that you see is the limestone, and that turns into marble. And marble is pretty soft. Like I said, it's the one that most of the sculptors like to use if you're working on porticus, I guess. I don't even know. I actually don't know. Buildings are often composed of marble, so you can carve figures or different reliefs or whatever into the stone, and it's fairly easy to do so. Now, quartz sandstone turns into quartzite, and it's very hard. It's very hard to carve quartzite, and I am not really familiar with any artists that actually use quartzite as a carving stone. Well, that's actually not true. I know that they carve some materials out of quartzite that they want to be really hard, like knife handles in ancient times were carved out of quartzite, or sword handles. Very expensive, obviously. And then we have other jewelry, if you want it to last a long time, that are carved out of quartzite. It's just we tend not to carve really large things out of quartzite because it's just hard to do. It takes a long time to do so. But the non-foliated textures in the rocks don't exhibit any kind of orientation of the minerals, so they look just like globs of minerals stuck in, and they have no airspace. They're much more solid. For example, limestone is broken pretty easily, marble not so much. The common non-foliated metamorphic rocks that we've talked about, or will talk about, or you'll see, are marble. We have marble here. We have the quartzites. We have the anthracites from the bituminous coal that's undergone metamorphism. You have the greenstones, the hornfells, just very dark in color. Greenstone obviously is green, and the hornfells is like a black, very dark colored rock. And I like the metamorphic chapter in the book because the book is made by professors from Michigan State, and they include the metamorphic zones of northern Michigan and the Wisconsin area. And it's very, very neat because you see the chlorite, you see sillimanite, which is at the center right here. If you went up into this area, it would be Lake Superior to the north here, obviously. And going out from there, then you have the sterilite right here. You have garnet, or the garnet sort of metamorphic zones where you're going to have some schists and things like that, and the garnets are going to be in there. You get the biotite or the mica schists, and then you have the chlorites, which are these, they look very green or chlorotic, which is yellowish green. And then you have basically the non-metamorphic type of rocks out here. And what's interesting about this area is we also have a lot of banded iron in this area, and we still don't know if it's metamorphic or not. There's some hypotheses that it was, these are old bodies of tiny microorganisms that utilized the iron that was found in the ancient seas, that the iron content obviously has dropped because they made it insoluble, and then when they died, they carried that iron with them, and it happened over many millions of years every year, and you had productions where you get this banding pattern occurred, but then some geologists think that it underwent metamorphosis, just like these other rocks that you find in northern Upper Peninsula Michigan. And here was the figure that I was saying remember, because you're going to see a subduction zone like the one you saw before, where I said the different zones where you'd expect to find different metamorphic areas, high pressure, low pressure, etc. And this we can predict pretty well. Get my pen. We can predict pretty well what's going to be produced based upon the depth, right, and the temperature under which that goes. Remember, some of these rocks aren't going to melt until you get up around 1200 degrees. So that's why this goes up to 1000. In most cases, we get some pretty advanced metamorphism once you get over around 800 degrees. And there's going to be some melting depending if there's a presence or absence of water, etc. But these are called metamorphic facies, which are large assemblages of the same metamorphic type of material, which suggested under or metamorphosed under similar conditions. And the question that I have in the notes is, how do metamorphic zones and metamorphic facies differ? And I answer that obviously, but metamorphic zones show the gradation of metamorphic change within a single rock composition, and metamorphic facies are groups of many different rock compositions whose mineral contents all indicate common temperature and pressure conditions during metamorphism. So metamorphic zones show gradation within a small area. Metamorphic facies show common groups that usually metamorphose together under similar pressures and similar conditions. The next slide shows you basically what I mean when I say that. So these are all different facies, which are areas where you would expect specific types of metamorphic rock. And so if you look, you would expect to find the green schists down here, which are going to be under, if you look back at this, it's going to be in this area where it's going to be near the surface, and the temperature is going to be relatively mild, lower. 400 degrees is not mild. And then if you look, which one of the students during the face-to-face section asked, well, look, it's really far underneath the ground. And yeah, that's true, but what they're looking at is the green schists that are over here. And they are between 0 and 25 kilometers below the Earth. And if you look where this green schist zone is, and then there's this dotted line right here, which means it's changing, you'll notice that we have the ocean, which isn't as dense as the crust over the top. Remember that the material in the oceanic crust is denser, but it's not as thick. And so you end up getting approximately the same conditions of moderate temperature, a lower pressure for these two zones, which means they produce very similar metamorphic rocks or metamorphic green schist facies. Moving on to the next slide, you'll notice that we have slate. Now, if you can afford a slate roof, good for you. I know I had a very wealthy neighbor, and I mean really like a billionaire, kind of strange as he was my neighbor, but it's his hometown and I live next to him. But he built a garage across from where his house was, and he put slate on top of it. And I asked him, if I wanted to do that on my house, and he said it cost him $1,500,000, which was pretty astounding. But obviously my house was not even near worth that much. My roof would be worth more than me. So anyway, it was interesting. But it's very expensive. But the reason it's expensive is because it lasts a long time. As long as it doesn't get broken, it's not going to weather as fast as the type of shingles that we use. Well, and we use asphalt shingles. The ones at my house would not last as long as the slate. Although slate does weather, it's not going to weather as fast as our asphalt shingles. And then the picture of the Taj Mahal, they took a microslide of marble and show it to you, and you can see how the different minerals, they're round, they've been pushed together, there's not a lot of available space there, but if you were to drop acid on this, it would effervesce and it would break down rapidly. And then there we have the metamorphic mineral resources, include the graphite, talc, asbestos, and the garnets. We also have contact metamorphic zones that you will pull specific minerals containing certain metals into the surrounding country rock, and the metamorphic rock then becomes a mineral resource. We also have water that will carry minerals across zones, which then will be deposited. Think of it like a underwater vent, where a lot of this material is moved through the surrounding rock, even though it may not be it's metamorphic rock, it's not actually igneous rock, and it will deposit copper and gold and a bunch of other metals. And of course, metamorphism and natural resources. You have the different metamorphic rocks through contact metamorphism, just like I talked about. And we have iron, which of course, like I said, we don't quite sure if that's metamorphic rock or what causes it, but we have the banded iron formations in Michigan, which could or could not be metamorphic. It's still under debate. And then we have the copper. If you go out west, there's quite a lot of mines where they mine the bornite and the chalcopyrite. And then galena, which is the crystals. Now this is a mineral, but these are crystals that are formed during metamorphism, and they get bigger. And tin and tungsten and zinc I'm not really familiar with, but I'm sure it's the chief sources of those come from specific metamorphic zones. Conclusion slide, which is metamorphism, the transformation of rocks without melting, usually beneath Earth's surface as the result of heat and pressure and fluid activity, produces metamorphic rocks. It produces 3 different types of metamorphism. So 3 principal agents of metamorphism are heat, pressure, and fluid activity, and they produce 3 types of metamorphism, which are contact, dynamic, and regional. Obviously, regional is probably going to be the most common because it's just where rocks have been subjected to heat and pressure, where contact is in direct contact with a metamorphic zone, and dynamic is going to be under changing conditions, probably low temperature, high pressure. And then metamorphic rocks are classified principally according to texture. Metamorphic zones show the gradation of metamorphic change within a single rock composition. Metamorphic facies are groups of many different rock compositions whose mineral contents all indicate common temperature and pressure conditions during metamorphism. And we have these index minerals as well. And metamorphic rocks contain many mineral resources. So pretty general, so you want to study a little more in depth, but overall, the metamorphic rocks I think are the most interesting to me, but we'll see. You guys can go through your collections in your kit. So that concludes this lecture. I hope you enjoy it, and let me know if the microphone is doing what it's supposed to do and it's not too loud. Thank you.